Hey, welcome back to science. Today's video is an interactive lesson. So you need to go grab a whiteboard or grab your notebook or something. I'm going to ask you to make 4 drawings today. Just do it. You will be better off if you have your brain activated by participating in this rather than just passively sitting back and watching. Or worse yet, fast forwarding to the good parts. Don't do that. Don't cheat yourself. Okay, what we're looking at today is fluid pressures. In particular, we're going to look at gas pressures because it's very convenient that we have a gas literally all around us. The air. I have a block of wood right here. Our first drawing is simply, how do you think particles of a gas are interacting with this block of wood as it sits there right now? That's all I'm looking for. How are the particles of the air interacting with this block? Pause the video, draw that one for yourself now. Okay, one of the most common ways that people draw this is to draw it like this. This is totally fair. We know that particles of a gas are moving in all sorts of directions, so they're going to be hitting at this in all sorts of different angles. Some particles are going to be moving faster, others are going to be moving slower. This is totally reasonable. However, as fair as this is, I actually want to simplify this to something that will be a little bit more useful for what we're doing. Let's instead just let's consider just the forces that are acting perpendicular. If we break this up into just the perpendicular forces, perpendicular things that are hitting, then it seems that it's reasonable that the push on this side is the same as the push on this side. If you're one of those awesome students that also said, hey, there's got to be some pushing down on the top, great, nicely done. I'm glad you recognized that. The key here, the most important thing from this, is that the pushes on this side are equal to the push on this side. To make this easier, I'm drawing them all the arrows the same length, even though we know some are going to be pushing a little bit harder, some are going to be pushing a little bit smaller. We're trying to kind of represent the average on each unit of area on this. Forces on a unit of area. I think we had a name for that. Pressure. Did the pressure get you on that one? Good. So the pressures are equal and this thing seems to be sitting there. Next drawing. What happens if there's a breeze blowing on this block from this way? So say I set up a fan or I just blow on this thing right here. Show me what the gas particles interacting with this would look like when there is a strong wind going this way. Pause video now, make that drawing. Okay. Hopefully your drawing looked something like this. Now, admittedly, there's another way that some people choose to draw this. Some people draw the arrows longer on this side. They draw the same number, or they draw more arrows and bigger arrows on this side. All of those are consistent. I'm not 100% sure right now that we can make a claim as to what is true. What we can claim is true for sure is that there's more overall force on this side of this block. If there's a bigger force on this side of the block than there is on this side, well then what's going to happen? Hey, we can demonstrate that. Ping pong balls are going to represent the air particles, and I'm going to have them hitting on this side. Since we're saying there's more pressure on this side, I'll just hit from this side. What a surprise. When the force was larger on this side, when the pressure was larger on this side, it pushed this block over. Please notice something really, really important here. These particles that are representing particles of air can only push. They cannot pull. There is no way for me to shove this thing into it and have it pull back on it. That's not going to happen. It pushes. Particles push. They cannot pull. What's more, you'll notice something else. Since we said the pressure on this side is larger than the pressure on this side, this leads us to a very important rule. Fluids flow. Fluids mean not only gases but also liquids. This is true of both. Fluids always flow in the same direction. This is a familiar sound for you. Fluids flow from higher pressure to lower pressure. From higher pressure to lower pressure. Just like electricity flows from higher voltage to lower voltage, just like thermal energy flows from higher temperature to lower temperature, we call that heat when it does that, and just like water flows from higher elevation to lower elevation. Everything that flows goes from higher something to lower something. It's a theme in this class. Okay, drawing number 3. We've got a Ziploc here. Got a little bit of air in it. It's not completely full. It's certainly not bursting. It is sealed. I'm going to leave it sitting there. I'd like your drawing to be the particles both inside and outside this baggie as it is sitting there right now. Pause the video. Go ahead and make those drawings now. Okay, let's see what you got. Hold it up so that I can see it, please. Oh, nicely done. Okay, so let's take a look at what the most common is through the class. Most of them look something like this. You'll notice there's an equal number of arrows pushing out as there are pushing in. Why does it have to be that way? What would happen if there were more arrows on the outside than there were on the inside? And that's a very common thing for people to say that has some logic behind it. People will say, well, gosh, there's a whole lot more air in the room. But remember, we are only worried about the particles that are interacting with the walls of this bag. What would happen if it was different? Well, we learned last time that if the pressure on the outside was bigger than the inside, the walls would collapse. This baggie is not collapsing. The walls are not collapsing. Neither is it pushing outward. So since it's not moving one way or the other, fluids are not flowing, that must mean that the pressure inside is the same as the pressure outside. And the only way I can think of to show that is to have equal numbers of arrows, equal size inside as outside. Did you have that? If so, awesome. If not, ask yourself what your thought process was. And let's move on. For our final drawing, we're going to take a basketball. This basketball has been inflated to 10 psi. I don't know what that means, but it's inflated to 10 psi. I'm going to do a quick demonstration here. If I push on this thing, I can indent it, but as soon as I let go, it pushes back. So I can squeeze the basketball, but it pushes back out as soon as I'm done pushing on it. That might be of significance. Go ahead and make one final drawing. Pause the video now, make that drawing. Let's see what you had. Again, hold it up so I can see it. Ah, excellent. Can you explain that to me? Or explain it to any family members that are nearby, or the dog. I don't care. Excellent. So, let me quick review what I just heard from the class in general. The consensus seems to be that we have to have more arrows on the inside than on the outside. I'm a little bit confused here though, because I thought if the pressure was higher on the inside than it is on the outside, that would mean this thing is moving out. It does not look like it is moving out. What's that? Oh yeah, good point. When I pushed on this and then let go, it did indeed move out. Right now, it must be that the skin of this basketball, the layer of the basketball itself is holding it together. Kind of like a balloon. A balloon does not hold as well. It's not as strong as the outside of this basketball, which is why balloons break a whole lot easier, which is why they'll expand more. But there is some tension in that balloon, and there's definitely some tension in the skin of the basketball, or volleyball, or football, or hockey puck. What are hockey pucks inflated to? I'm not sure. So what the heck does that pressure mean? When we say that this is inflated to 10 psi, or when we take a bicycle and say that the wheels of this are inflated to 25 psi. What the heck does that mean? Does that mean the pressure on the inside is 25 psi? But what would you call the pressure on this baggie? Wouldn't we call this 0? And you just did a drawing that showed that there was pressure on the inside of this thing. Perhaps the meaning of that pressure is the inside pressure compared to the outside pressure. So if this has a pressure of 10 psi, that means the inside is 10 psi greater than the outside pressure. That's interesting. That's a possibility. We might go with that. In fact, I think it works. Next biggest question is, what the heck is the pressure of the air as we're sitting here? Because I don't feel it. It can't be very much, could it? I guess that'll be for our next video. Till then, take care. See ya.